Hello everyone. In this video, we will learn about strongly connected components in a graph. So in a directed graph, a strongly connected component is a subset of vertices where every vertex in the subset is reachable from every other vertex in the same subset by traversing the directed edges. So if you will look into this graph, there are two strongly connected components. So one component that belongs to this node 1, 2, 3 and 4 and another component belongs to the subset of nodes 5, 6 and 7. This is a strongly connected component because every node is reachable from every other vertex. For example, if you will start from 1, you can reach all the other nodes 2, 3 and 4, and same for others as well. So if you will start from 3, you can reach all the other nodes as well, right? So this is a strongly connected component. Same for this one, you can reach all 3 nodes from any of this node, right? So if you will start from 7, you can reach any of these 2, right? And same for others. So this is also a strongly connected component, but same cannot be said for 1 and 5. So you can reach 5 from 1, for example 1, 2, 3, 4, then 5 through this path, right? But same cannot be done in reverse. For example, if you start with 5, you cannot reach 1. There is no path from 5 to 1, right? You can just you will just move into this loop. There is no path from 5 to 1. Hence 1 and 5 cannot belong to the same strongly connected set of components. So it has only 2 components. If you will look into the connectivity, so the difference in connectivity and a strongly connected component, one is connected to 5 but one is not strongly connected to 5 because 5 can be reached by 1 but vice versa is not possible, right? So connectivity in an undirected graph refers to whether 2 vertices are reachable from each other or not. So let's say one from 1 we can reach to 4 and vice versa, right? So they are connected to each other. Similarly, 5 and 7 are connected to each other. Although the path is different, you go to 6, then 7, but from 7 you can directly go to 5. The path is different, but they both are reachable from each other, right? So they are connected. Hence, a strongly connected component is a subset of vertices where each vertex is connected to each other. A subgraph of a directed graph is considered to be a strongly connected component if only if every pair of vertices A and B there exists a path from A to B and a path from B to B. Strongly connected is applicable only in directed graphs because in undirected graphs, for example, these arrows were not there. There was just simple lines in directed graph, right? So in undirected graph, if there is a line from one node to another, like both the nodes are reachable from each other, right? So here you can only move in one direction, in the direction of the arrow. But in an undirected graph, you can travel in both the directions, right? You can go from 4 to 5 and 5 to 4. So there is no concept like this because any edge makes the node traversal by each other. So this concept is only for directed graphs. Let us first look into the applications of strongly connected components. It is used in web crawling and internet analysis. So for example, site has many links. So it helps to understand the structure of the internet and subsets like World Wide Web. For example, let's say there are 3 websites A, B and C. So A has a hyperlink to B, then B has a link to C and C has a link back to A. So this represents a directed graph, right? So using the hyperlinks we can form the edges and pages can act like vertices, right? So from A we can go to B, then we go to C, then we come back to A. So this is a strongly connected thing, right? So it's the same thing. It's forming a cycle like this, right? So from B you can reach to any other side. Similarly from C you can reach to A and B as well. So this is forming a strongly connected component in the internet, right? So it is used to find these tight connections, these connections between the pages. So crawlers like Googlebot and all use this concept to find this connection between the pages. It helps them to prioritize crawling within the clusters and detect isolated and unreachable pages. For example, let's say there is a page which cannot be reached by any other page. For example, let's say there was another page called D and all these pages do not have any link to that page, right? So that is an isolated page. It helps to find this Googlebot and crawlers to locate these isolated pages as well. So social networking analysis. So to find the friends, so if you will if you're aware of Instagram and all this Facebook and all, so A is a friend of B is a friend of C, and C is a friend of D, like that, right? So there it forms a graph, and based on that, it gives you recommendation of friend suggestions as well. For example, if you know B and B knows someone else, then it recommends you, like B is a friend of C. It gives you the recommendation to be a friend of C as well, right? So a strongly connected component helps there as well. It's used in those platforms as well. Similarly, for software engineering, module package dependencies. For example, let's say there are different packages, and we import another package in a package, right? For example, there is a package A, B, and C. Again, the same thing, and A is imported in B is imported in C, and so on. So it forms the graph and dependency there as well, right? So it helps you find the cyclic dependency in the packages. For example, there cannot be cyclic dependencies in the packages, right? It will break your code. So in the large projects, it's very difficult to keep track of what module is dependent on what module, right? So there they use this type of algorithm to get the cycle and break it actually. Similarly, in the recommendation systems, the strongly connected components can help. For example, in some kind of shopping app, let's say they want to recommend you products. So, for example, let's say they have something like that. For example, there is a product called X, and people who purchase or like look for a product X, they also watch for Y. So let's say if you watch for product X, they will recommend you Y as well. Like they will assume that if you are interested in X, you might also be interested in Y as well, because that's the common trend among the people, right? So they use this kind of analysis using this strongly connected component behavior. Compiler design as well. It optimizes code execution path and perform loop detection. So for example, let's say this is a small loop, right? So in the graph representation, it will be looking something like this. So there is a loop condition, then if block, then we go to continue and back to loop. So this is a kind of a loop, right? So this package forms a cycle in the code, right? So this forms an SCC. So the compilers use this kind of strongly connected component to find and identify the loops and unroll, or they use it to optimize loops and variable lifetime as well in SSA form. Similarly, in same kind of manner, it's used in electric circuit design. For example, in a circuit, output of a gate is input to B. So in a circuit design, there are many gates, right? And output of a gate can be provided as input to another gate, right? So it's used to find the loops and things there as well. For example, let's say there are 4 circuits, similar manner. A's output goes to B, B's output goes to C, and back to A. So this circuit designers use this to find out the loops and all, and they ensure stability of the circuit, optimize the digital logic gates, so and avoid oscillations and infinite loops and everything. So similar approach, but it's used in many applications. Now let's see why DFS does not work in case of SSC. So your first thought might come like, if we can use DFS to find an SSC, but it will not work. So if you are not aware of DFS, I'll just come up with an example. We'll just go through it. So let's say we have this graph, the same graph, and we will just perform DFS on this graph. We will first start by 1. So in this graph, we already know there are 2 strongly connected components, which is 1, 2, 3, and 4, and another component is 5, 6, and 7. So in DFS, we start by a node and we just traverse it until all its neighbors and children are visited. Then so let's start by 1. So by 1, we can only go to 2. So if we have multiple options, we will choose one path, and we have only one path here, so we go to 2. From 2 now we can go to 3. From 3 we can now go to 4. Now from 4 we can either go to 1 or 5, but 1 is already visited, right? So we go to 5. From 5 we can go to 6, and from 6 we can go to 7. So as you can see, from 1 we can traverse all the nodes of a graph. All the nodes are reachable by 1, but as we have seen earlier, only these 4 nodes forms an SCC, and these 3 nodes form an SCC. But from 1, all the nodes are reachable, right? So if a node is reachable from a node using DFS, it doesn't mean that it forms an SCC with that node. So here as well, 5, 6 and 7, all of these nodes are reachable by 1, right? But they do not belong to the same SCC 1 belongs to, right? Because the vice versa is not possible. So now you must be thinking we can do the same thing with 5, right? So if 5 is reachable by 1 and vice versa, then they can belong to the same SCC, right? So that's what we will be going into doing into this brute force approach. So this is our brute force approach, which forms an SCC, and it uses the same DFS thing. So what we do here, using the DFS, we just find out, we just create a table. So here we have 5 nodes, so we create a table of 5 by 5, and the output of this table is what node is reachable by what. So through 1 you can reach all the other nodes. So through 1 you can reach to 2, you can visit 4, 5, and you can visit 3 as well, right, from this path. So from 1 you can reach all the other nodes. From 2 you can reach 3, 1, 4 and 5. So all the other nodes can be reachable by 2 as well. From 3 you can reach 1, 2, again all the nodes. But from 4 you can only reach 5. So hence the 2 is with 4 and 5. And similarly from 5 you cannot reach any other node, right? So false for 1, 2, 3, 4. So this part of code, this loop for you in 0 to 9, this whole loop is just building this matrix. After we build this matrix, we just initialize our SCC list, which is this grid I have written here with an empty, and initially it will be empty, and we have a visited nodes array which will also be an empty. Now we will start with one node, any node we can start, and we try to find out if the neighbor as well as the node are reachable from each other or not. If yes, we just form an SCC with them, otherwise we don't. So for example, we start by 0, so we start by 1. So if you go through the code, if the node is already visited, for example, if the node is already processed, then we don't do anything, we just continue. Otherwise we form an strongly SCC with it, then we visit all its neighbors, and we just check if the neighbor as well as the node is reachable from each other or not. So if reachable UB and reachable VU, we form we also append the V to the same SCC as U, and we mark the V as visited, and so on. So for example, let's start with 1. So 2 is reachable by 1, and 1 is also reachable by 2. So for 1 2, this is true, and 2 1 is also true, right? So they form an SCC. So we will form one SCC here, 1 2, and we will mark 2 as visited as well. So let's mark this place true, and 1 as well true. Just a second. Now we will continue with another neighbor, other node is 3. 3 is also reachable by 1 by this path, and vice versa is also possible. So 1 3 is true, and 3 1 is also true. So 3 will also belong to the same SCC. Sorry, 3, and we will mark 3 as visited as well. 2. Now 4. 4 is true, but 4 1 is not true. Same with 5. 5 is true, 5 1 is not true. So they do not belong to the same SCC, and we don't mark them as visited. Now for 2 is also already visited, so we skip it. 3 is already visited, we skip it. Now we come to 4. Now 1 is not visited, right? 1 we see that 1 2 3 are already visited, right? So we just skip them. We look for 5. Now 4 5 is true, 4 5 is true, but 5 4, which is not true, right? So they cannot belong to same SCC. So only 4 will be forming a single SCC. I'll just put 4 here and mark it as true. Now the 5 is the remaining node, and it will be forming a single SCC as well, and it will mark true as well. So that's what we are doing in this algorithm. We just create this matrix using DFS. We find out how many nodes and what nodes are reachable by what node, and we just compare with we just pick up a node and we compare it with all the nodes. Whatever node is reachable by the For example, we pick up a pair of u and v, and we see if u is reachable by v and v is reachable by u, we just form an SCC with them. So if you will look into the time complexity, it will be v square, right? Because here first of all we are using DFS to build this table, right? So for each node which is not visited, we perform a DFS. So a DFS will take v plus e time. So the time complexity of DFS is v plus e. V is the number of vertices and e is the number of edges present in a graph. So if you look here, when you perform DFS using 1, right, you visit all the vertices, which represents v, and you go through most of the edges, right? So which represents e. Hence the time complexity of a DFS is v plus e, and we are performing DFS for every node, right? Hence the time complexity for this first part of algorithm is v into v plus e. And the second part of algorithm, we just pick every pair and we just see if the pair is connected with each other or not. So the number of pairs that can be formed are v square, right? So the complexity for the second part of the algorithm is v square. Hence the total complexity of this algorithm is v into v plus e plus big of v square. Now let's look into the Kosaraju's algorithm. This was an algorithm to optimize this approach, to reduce the complexity to find an SCC. In this, we perform a DFS on the original graph and store the finishing times. So we perform a full DFS traversal of the graph. After visiting a node and all its descendant, we push it under the stack. So we make the use of stack here. After we process all the nodes and push all of the nodes in the stack in the descending order. For example, the node which will be visited first will be on top of the stack. After we'll just take a look into this with an example, then you will understand. After that, we just transpose the graph. For example, we reverse all the edges. For example, in the original graph, if 1 is connected to 4, we reverse this edge. 4 will be connected to the 1 and transpose of the graph. After that, we perform another DFS and that will give us an SCC. So let's look into this algorithm by using the example. We have this graph here with the 5 nodes 1, 2, 3, 4 and 5. So let's start with 1. As we know, 1 is not processed fully yet because it has edges to 2 and so on, and 4 as well. So we can go to 2 from 1. Similarly, we can go to 3 from 2. So you can see in this graph from between 2 and 3 there is a right. You can go to 3. Now if you look into the 3, 1 is already visited, right? So from 3 we cannot go anywhere else. There is no other path. So 3 is fully traversed. We push it into the stack and we pop it. We just move back to 2. Now from 2 as well, as 3 is already processed, we cannot go anywhere else, right? So we push 2 in the stack as well and we move back to 1. Now from 1 we can go to 4. So we move to 4. From 4 we can go to 5. Now 5 is fully processed, right? There is no edge from 5 to anywhere else, right? So we just push 5 into the stack. Similarly, we move back and push 4 into the stack, and we move back and push 1 into the stack. So if you will look into our stack, has the elements in decreasing order of the time. So 1 took maximum time to get traversed, right? So it's on the top of the stack. Now step 2 says traverse the graph. So our original graph was like this, right? So traversing of the graph is just reversing the edges. So the traversed graph will be looking something like this. So here each edge is reversed. So 1 was connected to 2, here 2 will be connected to 1. So every edge is reversed. As you can see, every edge is reversed. Now in the step 3, we make use of the stack we already had, and we just make use of a visited array as well. So we start popping the elements out of the stack. So let's say we pop the element 1 from the stack, and we just do the DFS again. So we keep on popping elements out of the stack and we perform DFS on them. So let's say we pop 1 out of the stack and we perform DFS on the transposed graph. So if we perform the DFS using 1 on this particular graph, what do you see? We can from 1 we can go to 3, then 2, and from 2 we cannot go anywhere else because 1 is already visited in DFS, right? So we come back, then again come back, and done. So from 1 we can only traverse these 3 nodes, right, using the DFS. We cannot go to 4 and 5 anymore because of this transposition. Hence these 3 nodes will form an SCC. And same thing here. So I just popped out the 1 from the stack, and using DFS we saw that 2 and 3 are visited by 1, so they form an SCC. So we form an SCC using these 3 nodes, and we mark them as true in the visited array. Now we pop 1 out of the stack. Next element is 4. Now from 4, as you can see, we can go to 1, 3, 2, and all these nodes are reachable. But as we know, all these 3 nodes are have already formed an SCC because their visited array is true. They are already part of an SCC. So we will just not go in that direction because we just go to a node. While performing the DFS in this approach, we just go to a node which is not already visited. So from 4 we have only one option, 1, which is already true in the visited array, so we'll not go there. So we have no other path for 4, so 4 will be coming out of stack, and 4 will form an SCC alone. Similarly for 5, as 4 is also visited now, 5 will also form an SCC alone. Now all the nodes are visited in the array, right? So we have our SCC. We have 3 SCC components in this graph, which is 1, 2, and 3, 4, and 5. As you can see in this graph, these are the components only. So if you will look into this approach, this is much better than the brute force approach, as our brute force approach was taking v square plus v into v plus e complexity, right? This was like quadratic complexity. Here the complexity is linear, which is v plus e, because we are on all the 3 steps, the complexity does not exceed by a DFS complexity. In this first approach, we are just performing a single DFS, right? In the brute force approach, we were performing DFS for every node, hence the complexity of v into v plus e. But in the first step, we just perform a single DFS here, so the complexity of first step is v plus e. Transposition of a graph is just reversing the edges, right? So you just visit each edge and reverse it, right? So the complexity here is e, simple e. Similarly, in the step 3 also, we are just performing a single DFS. So here it seems like you are performing DFS for multiple vertices, but as you can see, once we perform a DFS on a node, we do not come to it by other node. For example, we started with 1, right? So we visited 2 and 3, and then we make them true in the visited node. But when we started with 4, we did not visited 1, 3, and 2 because they were already part of SCC, right? Which means visited was true for them. So these will not be visited again. Hence, every node and every edge in this DFS as well is processed only a single time. So the complexity of the third step is also v plus e. Hence the complexity of this whole algorithm becomes 3 times of v plus e. As we remove constant while calculating the complexity, it is only big O of v plus e. Now, as you have realized, the complexity is reduced by a large amount, but we are doing the traversal of graph 3 times. One for first step, and the second step we transpose it, and the third step again. So to reduce this, we have Tarjan's algorithm, which will find the connected components, SCC components, only using one traversal of DFS. We don't need to traverse it again and again. I will be covering that in another video because this video is already getting long, and explaining the Tarjan algorithm will take some time. It's a complex algorithm. So I will be covering this in a separate video. Thank you for watching this. Please like, share, and subscribe.